Welcome to Titan Building Block 6M PCSC Machine Fab Edition. So, in your setup, it's going to be very similar to 5M. Our work coordinate system is going to be top, front, left corner of our stock. Our stock's going to be fixed size box X width 2.05. That is basically the minimum amount that we need to make this part. Any larger is going to be a little bit wasteful. 2.1 is probably a little more obtainable on the saw, but do your best to get it. 2.05, definitely no less than 2 inches, because that doesn't leave enough room to do any machining. Y depth is going to be 2, Z depth is 1, because we're using the same size stock. And very important to make sure that you have it offset from top 30 thousandths, because we just want to take a little skim pass, and I'm only talking to the couple students that have buried the shell mill into the top of this part because they leave this offset, and they don't leave it offset, it's centered. We do not want this. We do not want our model centered in our stock in the Z direction because that is way too much of a cut. So, make sure it's offset from top, and 30 thousandths is just enough to take off, clean up the top surface of our part. Our stock size verify is going to be 2.05 by 2 by 1. Post-process is going to be preferably 6001. Program comment 6M S1 with your initials. Make sure you're still updating this comment section, because if you're just copying everything over, you might forget about this, and then what else are you possibly forgetting? And we're going to use our work offset number 1G54, and this is basically the exact same work offset as Titan 5M, so we don't have to do any additional probing whatsoever. So, in review, work coordinate system, top, front, left corner, stock size, pretty much the standard. Make sure it's offset from the top, especially if your initials are ZP. And that's it. The first operation, nothing new and fancy about this one. We've done it before. I'm not going to spend any time. If you're not sure about this, you're making me nervous. Go back and look at some previous videos. We're going to simplify this a little bit. We're not going to use our 3/8 flat end mill because we're running low on them. And sometimes it takes a lot of time to change tools. We're just going to do all of the 3D adaptive work with a 1/4 inch flat end mill. We're going to have to take light cuts because we do not have the rigidity of the larger diameter tool. So you can copy the 3D adaptive from 5M and just change the tool and then tweak a few things. So we're going to be using tool number 3, 1/4 inch flat end mill, flood coolant, 6,000 RPM. This is going to be going at 126 inches a minute. That will be 7 thou feet per tooth. Lead in, 100, lead out, 100, rapid plunge 20. And you're like, whoa, 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 that's really fast for that small end mill. But wait, we're going to, I'll go over that on another tab. Just hold that thought. We're doing 3D adaptive, so we're going to have rest machining on. And obviously it's going to be from previous operations because we don't want to take care of the top of the part because the shell mill already did it. Heights, pretty standard, same thing. We're shooting past the bottom of our model. If you don't know why, go back and watch some other videos. We just want to make sure we're going a little bit past our model. Give us some clearance. I don't know if it's clearance, whatever it is, just do it. And our passes tab. So our tolerance is going to be 4 thousandths. We don't need to be super accurate on our roughing operation. Optimal load is going to be 0.05. This is what it's going to allow us to actually run our tool really fast because we're not taking a very wide cut as far as our optimal load width of cut. If I edit this expression, we're going to go 20% of our tool diameter instead of the default value of 30. So we're lowering our optimal load but still keeping our feed rate relatively fast. We're actually going faster than we would with a 3/8 tool, but we're definitely taking a much narrower width of cut. So 0.05 is the 20% times the tool diameter for the optimal load. Minimum cutting radius 0.025. Basically, that number will change how much our end mill can fit into this small space, so that is a default value 0.025. Don't worry about that, don't worry about climb. Maximum roughing step down 1 inch, that's our flute length. Fine step down 0.1. Minimum step down 10 thousandths. Flat area detection, I don't even know if we need this on, but what the heck, we'll just check the box anyway. And we're going to leave stock because this is a roughing operation, not a finished one. So we're going to put 15 thou radial and 10 thou axial stock to leave. And we're going to put 2 thousandths of smoothing. If you don't know what smoothing is, really doesn't matter. Just do it. Just makes our G-code nice and smooth. Allows the machine to move a little bit faster. It gets rid of unnecessary point-to-point G-code movement. So 2 thousandths of an inch for smoothing. And linking. Full retraction, preserve rapid movement. Most of this stuff will be fine as is. Stay down level most. Non-engagement feed rate is going to be the same as our feed rate. So change that or right-click on it and reset it to the built-in default. We don't need to be having the machine going up to faster RPMs. I mean, not RPMs, feed rates when it's not engaged. It's not moving very far, so there's not enough time for it to build up the speed to get to there. So we're just going to leave it as default. And of course, we definitely don't need to go slower. So we're going to leave it at our feed rate. Lead-ins, transitions, don't worry about that. We don't even really need to worry about any of this stuff because we're not really helical ramping into this part. We're entering from the outside. Click OK. And it's going to take some time to load. This is a good time to evaluate your life. Think about your plans after high school. Remember, everybody can make a mistake while machining. It's not if, it is when. So, now we got our 3D adaptive toolpath looking good. We got our toolpaths going around the outside for this whole part, and then we come in here, and this is where our minimum cutting radius goes. So that's good. It looks like we don't have any unnecessary extra linking moves. It all looks good. And then we're going to finish this operation. I don't know, tiny slow down. Slow is smooth and smooth is fast. So we need to clean up the outside with a 2D contour, of course. And this is copied from a previous operation, but we're not using the 3/8 flat end mill. We're going to get it done with the 1/4 inch flat end mill. Tool number 3. 6,000 RPM going at 60 inches a minute. Rest of that doesn't really matter. Geometry is going to be there, of course. Heights, obviously, is pretty much the same. We're going to go down an extra 5 thousandths for the bottom height based off of the selected contour. Passes, 4 tenths, because we're going nice and accurate. Cutter compensation is going to be in control. Finish feed rate, 60 inches a minute. And we're going to repeat a finish pass, do a little spring pass, take care of any tool deflection that may or may not happen. And all this other stuff we don't need. Linking up most of this doesn't matter. We could change the sweep angle 45 degrees. It's pretty good. We're just going to leave all this stuff. Most of the time, it's like not that important on this operation. Click OK. Right around the outside, but it's going to go around twice. And now we need to take care of this. Oh, I shouldn't have shown you that toolpath. Let's just watch the simulation. You don't have to wait till the very end to simulate. You can kind of just check as you go. There's our shell note. We know what that looks like. And here's our 3D adaptive. It's going to go around and around and around and around and around and around. And then, oh, it's getting close. It's getting close. There's our finish pass. But what about this? We could have the 3D adaptive go in here, but it's going to be such a small toolpath. There isn't a whole lot of room for our end mill to go in between these two pegs. And it would be like, and it just makes the machine like shake and kind of like a, this is not good for it. Let's learn a different way to do that. We could like do a 2D contour around this and just go plunge and go full width straight into this, but I'm pretty sure that's going to break that 1/4 inch end mill. Or we'd have to go like really slow. We are going to take a 2D contour and ramp around it. So 1/4 inch flat end mill, we definitely need flood coolant. Pretty much always going to use flood coolant, except for like that first operation with facing, so you can actually see what the heck is going on. Because sometimes the flood coolant really kind of messes up your visibility. 6,000 RPM, and the only thing that really matters on this is going to be our ramp feed rate, because we're going to be ramping in, and that will be a ramp feed rate. So I just made everything 60, just to kind of make it all the same. Geometry is going to be this middle bottom peg, arrow on the outside. Heights, all this is fine. Passes, cutter comp is going to be in computer. We are not using cutter comp in control on this one, so in computer. Finish is still 60. Stock to leave. We're going to leave 10 thou axial and radial. And linking. This is where the magic happens. We want to make sure we click ramp. And it's going to be a 4-degree ramp. It's going to be a 50 thousandth maximum rep step. I'm pretty sure it's step down. Ramp clearance height is going to be 0.02. Click OK. And that's going to allow our end mill to ramp round and around and around. Nice and smooth. It's not going to take a long time. It's not going to cause any, like, sudden on our end mill. So, we'll just go ahead and watch that simulation. It could technically maybe do this. Remember, you don't want to just simulate one thing. You either need to simulate everything, or sometimes turn the stock off so you can just look at the toolpath. Oh, we know that. Here we go. It's going to go like, because it's not cutting or anything right here, so it's going to, like, sound different. So it's just going down a lot more gentler than just plunging full width across, full steam ahead. And then there's that. Oh, and it's doing something else that I wasn't ready to show you. So the next thing is to do a 2D pocket. Titan does a 2D contour. You can probably do it. I don't know. It really doesn't matter too much. I don't think. I'm not an expert. I'm not getting like a lot of money to do this, so I think it's okay. And works for me, probably will work for you. So it's going to be a 2D pocket because we're going to clean up this floor, and it's also going to clean up the walls on our little pegs. We're still using the 1/4 inch flat end mill, of course. 6,000 RPM, 40 inches a minute. Nice and slow for a finish pass. Our stock is going to be, I'm just going to get rid of this so you can actually see what the heck I clicked on. So our geometry is going to be this surface. And then our stock contour is going to be that. Heights, all this should be the standard. We're not going any deeper. Passes, pretty sure all this is good. You can pause it, look at the numbers, but I'm moving on. Linking, we got a bunch of stuff, but like most of the time it really doesn't matter. We want to make sure that we're plunging. We don't need to do a helical ramp into like 10 thou material, so we can plunge straight down. And should give us a finish path that's going to clean up the floor and the wall. We could leave a little bit of radial stock and come back and do a 2D contour around each peg and use cutter comp, but it probably doesn't have to be that accurate. It's not really that important. Maybe it'll still be within the 5 thou tolerance on the drawing. I think it's 5 thou. I don't have the drawings in front of me right now. It's kind of a bad thing to do. I'm kind of just going from memory. So, it'll be good if you want to do pocket and then a contour to finish the floor and then the walls. Go for it. And now we're going to move on to spot drilling. We're going to use the 5/16 inch spot drill because that's already loaded in the machine. And we want to make sure that we chamfer this edge so we don't have any burrs, and we can't do that with our 1/4 inch spot drill because it's a 1/4 inch hole, therefore no room to actually chamfer. So we're going to use the 5/16 spot drill from one of the previous Titan building blocks that required the 1/4 thread. So we have a bunch of holes. We can't spot drill them all at once because these holes are going to require different spot drill diameter depths than these holes. So my first set of spot drills are going to be for the threaded holes. I'm not going to spend a whole lot of time on this because I'm pretty sure you are experts in spot drilling by now. Select face. Make sure you got your 5/16 spot drill, plunging at 20 inches a minute, 5,000 RPM. Finish your faces. Height's going to be bottom height. It's going to be from the whole top minus 0.1. And our drilling rapid out. Just a little boop, 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 boop. And now we want to do the larger 1/4 inch holes. Same tool, of course, same feeds and speeds. We're just clicking on different faces, and we're going to go a little deeper, I believe. Going to go negative 0.125, eighth of an inch, 125 thousandths. And click on the next tab. Okay. Spot drill right there. And now we need to drill our holes. First, we're going to drill the holes for the 1032 thread. That's going to be a number 177 drill. That's drill number 16, not tool 16. The drill size 16. Remember, drill bit sizes come in letters, fractions, or numbers. So this is a number 16 drill for a form tap 1032. It's going to form the threads, not to cut the threads. Get those things from a drill chart off the interwebs. There's our faces, of course. Obviously, make sure you're using the right drill size. Flood coolant, 30,000 RPM. Plunge, 30. Retract, 40. Just like before. It worked before, so it's going to work again. And then the height is going to be, bottom height's going to be whole bottom. Drill tip through bottom. And then we're going to do chip breaking. We don't need to do full retract. Click OK. 1032 tap. Make sure you copy your 1032 tap, not a 1/4 tap, because that will result in a broken tap. Or a bad hole. I don't know. Don't try it. Select your right hand tap the 0.19. That's the diameter, and this is like the threads per inch. Flood coolant, 1500 RPM. Geometry is the whole faces. And then the bottom height's going to be the whole top, negative 0.2, because I believe we need to have threads that are 0.150. So we're going to go down a little bit deeper because the bottom of the tap doesn't exactly cut really good threads. So we're just going to go a little bit deeper. Height is going to be right tapping, and we want to make sure that our hole is going deeper than the tap. We need to make sure we got clearance so we don't break the tap. This is probably a little too much clearance, but hey, what the heck, not going to hurt anything. Remember, we're just here to have fun, make some chips, maybe break some tools. Hopefully not like crash a spindle into the table and like rip the vise off the hoss. That would really be bad. And we're also going to be safe. Next operation is going to be drilling, and we're going to drill all the way through the bottom of the model. Not necessarily all the way through the bottom of the stock. So we're going to use our 1/4 inch drill. You're most likely going to have to set this up. There are plenty of sample tools that you can pull from. It's basically going to look like this drill bit right here. Edit. Let's see. 0.25 1/4 inch drill. Cutter. It's all here. It's all really fancy. You really don't need to do most of this. Most important thing is going to be diameter. And honestly, you really even don't need it because the hoss is just going to drill with the drill bit that's already loaded. And we don't have any like crazy collision stuff to worry about. But if you want to set it up, it's just like that. Actually, this one actually sucks. This should not be 0.25. The drill bit shaft is usually the same size as the drill bit diameter. So 0.25. But I'm not going to save it since I change my feeds and speeds and stuff like that. It's fine. Shaft, no holder. Yeah, we got a drill chuck holder. Probably not even going to hold it in this chuck, so you probably don't even need it. Feeds and speeds, 5,000 RPM, 40 inches a minute. I do think that's pretty much correct. And I believe tool number 7, I think. But remember, check the whiteboard for your tool numbers. I'm going to click cancel because I don't want to change anything. And we're going at 5,000 RPM, 40 inches a minute. Retract feed rate 40. We could retract a little bit faster, but it's not really saving us that much time. Geometry is going to be our selected faces. And the heights. We're going to go bottom height. We're going to go whole bottom. Drill tip through bottom. And we're going to break through depth 0.05. This is basically how much that end mill is going to shoot through the bottom of our hole and break through just the tip. So we want 0.05, plenty. We could also do like stock bottom, and here's our bottom of our stock, and there's our how deep it's going, but we really don't need to do that. That's just like extra drilling. So we're gonna go whole bottom. Sometimes it's handy to drill all the way through the stock. This time, I don't think it's handy at all. We're doing chip breaking, partial retract. We don't need to do full retract because we're not really drilling that deep, and we do have a rather somewhat quote large drill bit for what we use. We don't use a lot of big drill bits, so this one is kind of in our large category. All this stuff is probably fine with the default values. Click OK. And we're not tapping these. And we're going to finish with our tool number 9, 1/4 inch chamfer, 10th out edge break. You know the drill. Copy it from before. 4,000 RPM, 50 inches a minute. Geometry, all those things. Make sure the arrow's on the right side. Heights, pretty much that's fine as is. Passes, chamfer width, 0.01. I did change the tip offset from 0.08 to 0.06 because we don't have to get into really tight areas on this part. It's going to be kind of tight when the chamfer's coming around right here, and we won't hit that. But by moving this number, it kind of positions our chamfer to cut at a different spot on the cutting edge so that one section is not getting worn out all the time. Even though we're milling in aluminum, it might not even matter, but it's just kind of good to really know what this tip offset actually does. Franking, all that stuff is fine. Click OK. I probably should have told you to save your work like a bunch of times while you're doing this, but you should know better by now to always save your work, even though Fusion's great and autosave works, but our computers, especially the ones that have the blue screen and death issues, you know what I'm talking about. We need to make sure we save often. So we got all our toolpaths. Gonna go ahead and turn off the visibility of my model. Gonna go to simulate, make sure I'm simulating everything. We got our stock, we got our work coordinate system, top left, front edge, simulate. This is all good. I'm gonna go toolpath, gonna change it to tail so it disappears. This is other stuff that you can do. This is good stuff on collision. That's always good to know if you collide into your part. Info, statistics. So, 7 tool changes, 11 operations, machining distance 271.648 inches, and an estimated machining time of 6 minutes, 8 seconds. I'm going to leave this on. Info. Play. I won't do that anymore, I promise. Okay, there's our facing, then there's our adaptive, looking good, you know. Got plenty of room on the bottom for our talon work holding on the carrier that will be moved in setup 2. There's our 3D adaptive, making constant engagement, full depth, 1/4 inch, flat anvil, doing work. We might break a tool, not gonna lie. We're using some dull tools donated from a machine shop. We got a bunch of them, and I did some test cuts, and it's making some significant chips. Might be able to go a little bit faster, but we'll see. We're definitely not babying it. Our mini mills gonna be running pretty fast. There's a finish pass, going around 2 times for that spring pass. There's our ramp, round and around. Remember, you can always left click and like scrub, whoops, easy, and like go back and forth, kind of slow it down. It's not like you watch this as fast as you can. You want to stop and actually look and see what's going on. You can even like drag through here. You got things slow it down where it's kind of important. You can go nice and slow. There's our spot drill. Sometimes if it's going too fast, it's going really fast, and you're gonna skip over stuff. And you might not even see it because it's going too fast. Spot drill's looking good. If I turn my model back on, and display, transparent. I think that's lining up nicely with the chamfers. It looks good. There's spot drills. I hope you're not bored, because when you get bored, you get lazy, you get complacent, and you make mistakes. Check everything, trust, but verify. Slow is smooth, and smooth is fast. There's our drilling. Chamfer, 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 chamfer. And that's it for setup 1. And guess what? Setup 2 and 3 is the exact same as Titan 5M. Like, literally, you can just use the exact same G-code from 5M because it's the same size diameter. The height, I believe, is the same. You might want to double check with the drawing sheet, but I'm pretty sure we still have a top to bottom dimension of 3/4 of an inch. Let me top back into the model and verify that the distance top to bottom, 3/4 of an inch. That's the same as the previous Titan building block we just did. Back into cam. Oh no, it's gone, disappeared. Turn your visibility back on. Oh no, there's nothing over here. It's under here. There it is. I'm gonna save. And this is just gonna be a little kind of a, I think they call it, I don't know, Easter egg. Easter is right around the corner. But just to see if you're actually watching this video all the way to the very end and you're still paying attention because you're a student that values your education, I'm gonna show you some new things. In your setup folder drop down, we're gonna add some manual NC. We're gonna do a comment. Our comment is going to be WCS top front left. Click OK, and I'm going to drag this up to the very top. Don't worry about this, we have to regen because we're adding stuff even though we're not really changing the G-code. These are just comments. I'm going to add another comment. 35 foot-pounds for the torque wrenches on the Mighty Bite Talon grips. I'm going to take this, I can also just duplicate it, add it right there, edit. Oh, what else should we do? 25% rapid for first cut. You can bump up the rapids a little bit after your first cut. Remember, it's your first cut. That's the moment of truth as far as the correct work offset, your tool lengths. Feed rate's going to be 100%. We're up against the talon grips and the stop. I'm going to go back into this one. Front, top, left. Remember, our G54 is already set. What other manual comments do we have? Stop, we can do optional stop, dwell, tool break control, tool measure, chip transport, open close, we can't do most of that, verify clean, action, print message, display message, alarm, alert, pass-through, force, tool change. So, we're good with those. Cancel, so our comments are work coordinate system, top left, 35 foot-pounds, which will remind you to tighten it down with the torque wrench. 25% rapid for the first cut, and then we got our facing. I need to regenerate that. Remember, it's looking at previous operations because it's doing arrest machining. Another comment could be single block. Single block isn't going to hurt anybody, especially that first cutting operation. Make sure we're going nice and correct with our work offset, our tool numbers, and stuff like that. So if you're that student that needs single block, go ahead and put a little reminder in here for you to turn it on. Actually, yeah. And then post-process, remember, we just want to post-process the entire thing. I wish I had $100 for every student. That would just post-process the last thing they worked on. They got to the machine, they're like, I'm ready to go, and then there's basically everything's missing except for the last operation, because it's the last thing they did. You want to make sure that you have the entire setup done and ready to post-process G1, G2, our post-processor, next-gen control for the super mini-mill, not the regular mini-mill. You could get by with the pre-NGC on both of them. Program name or number is going to be 6001. Program comment, all the same. Most of this stuff is good. G187 is on at yes. And post. Desktop. Remember to save your work before you post. Hopefully it's not too late. Some of the laptops have been crashing at that unfortunate time. I'm going to save this on my desktop. And you need to look at your G code. This is where the machine reads all this stuff, and then it figures out how to move with the tools and do all the CNC stuff with the general and miscellaneous codes. Don't just post this and close this as fast as you can. This is basically what the robot needs to make your part. It is very important that you look at your G code. Tool 1, face mill. Tool 3, flat end mill. There should be no tool 2. We are not using the 3/8 flat end mill. Tool 4 is going to be our 5/16 spot drill. Phil, where's 5/16? Oh, it's a decimal. But don't worry, you're smart and know the value and importance and how to convert fractions to decimals. Tool 5 should be our .177 drill. Tool 6, our 1032, the right-hand tap. Tool 7 should be the quarter-inch drill. And Tool 9, our quarter-inch chamfer. Remember, all tool numbers are subject to change, and please check the whiteboard. Here's our manual comments that we added. Work coordinate system, top, front, left, already set. 35 foot-pounds, 25% rapid. And then we got our facing operation right here. 3500 RPM, G54. Here's that G187, which isn't even used during the facing, but it's there. And then we got our G code and all this stuff right here. And then we got our 3D adaptive, 6000 RPM. G54, it's going to use tool 3. And then there's all our code. We got a lot of it. And then we got a 2D contour and a pocket with not as much code compared to the 3D adaptive. Spot .177. Then we got our other spot drill because we're spot drilling the quarter-inch holes. And then we got the drill and the tap and probably some chamfering. And we're looking at 1,842 lines of code. Thank you. Good luck. PCSE Machine Fab, signing out.